Today, we're going to peel back this silicone on your favorite devices to uncover a hidden, high-speed world. We're talking about the secret communication network that makes everything work, and you'll see how it operates kind of like a perfectly tuned postal service, making sure every single piece of data gets delivered right on time.
I mean, just think about it for a second. Inside that tiny little processor in your phone, you've got billions of components, all split into different departments. The main processor, the graphics unit, the memory, you name it. And they all have to send and receive information constantly at speeds that are just, well, mind-boggling. So how do they pull it off without creating the world's worst traffic jam?
So here's how we're going to break it all down. First, we'll look at the information gridlock problem inside a chip. Then, we'll meet the digital postal service that was built to solve it. We'll get into exactly how a piece of information gets delivered, check out its express and secure mail options, and finally, we'll see why this unsung hero is the real key to the speed you see on your screen. All right, so first up, let's really set the stage and understand the problem here. Why do we even need a system like this in the first place? You know, every modern system on a chip is basically a tiny city. You've got your managers, like the main CPU, that are giving all the orders. And then you have the subordinates, like memory or the graphics unit, that have to carry out those orders. Now, if you don't have a common set of traffic laws for all this information zipping around, it would be absolute chaos. And that's exactly why a high-performance protocol is so crucial.
So how do you solve all that potential chaos? Well, you introduce a set of rules, a protocol that everyone agrees to follow. Let's meet our solution. And that solution is a protocol from ARM called AMBA AHB. It stands for Advanced Microcontroller Bus Architecture, Advanced High Performance Bus. But you can just think of it as the official rulebook for our digital postal service. It defines the exact process for addressing, sending, and receiving data, making sure that information flows smoothly at crazy high speeds. In this system, you've really got two key rules. First, there are the managers. Think of components like the CPU that kick off requests. They're the senders, the ones writing the letters and putting the delivery address on the envelope. And on the other side, you've got the subordinates, things like a memory controller or a USB port. They're the recipients, the ones responding to requests by sending data back or just confirming that a delivery was made. Now that we've met the players, let's actually see how a single piece of mail gets from a manager all the way to a subordinate. So every single delivery happens in a few clear phases. First up is the address phase, and this lasts for just one single tick of the system's clock. This is where the manager slaps the destination address on the envelope. Next is the data phase, where the actual package of data is sent or received. Now this can take one or more clock ticks. And finally, the subordinate gives a confirmation that the delivery is complete and the whole system is ready for the next one.
These technical signal names might look a little intimidating, but trust me, they map perfectly to our postal analogy. HADDR, that's just the destination address. HWrite tells the system if we're sending a package or receiving one. HW data and HR data are the actual packages of data themselves. But the really important one here is HReady. That's the delivery confirmation. It's the signal that tells the sender, yep, your package has arrived, and it keeps the entire system perfectly in sync. And this quote right here from the official spec, this reveals the system's secret sauce. It's called pipelining. What it means is that while one package is still being delivered, the system is already getting the address ready for the very next one. Just imagine a mail carrier who has the next letter in their hand the exact moment they drop off the previous one. There's literally no waste of time. This constant overlapping of tasks is what lets the bus run at such incredible speeds.
Okay, a basic delivery is great, but sometimes you need special services, right? Well, our digital postal service has a few tricks up its sleeve for that. First up is the burst transfer. Imagine you need to send a bunch of data to memory addresses that are all right next to each other. Well, instead of addressing each one individually, a burst transfer lets you send just one address and then say, hey, deliver this package and the next 3 to all the houses in a row. It's incredibly efficient, just like a mail carrier delivering flyers to an entire block without stopping. And these bursts come in 2 main flavors. An incrementing burst is the simple one. It just delivers to addresses in a sequence, like going down a street from house 1 to 2 to 3. A wrapping burst, though, is a little different. It's designed for fixed-size blocks of data. So if you need data starting from the 3rd apartment in a 4-apartment building, it'll deliver to 3, then 4, then wrap around to deliver to 1 and 2, making sure you get the whole block as fast as possible. And then there are locked transfers. This is the high-security armored truck delivery. When a manager kicks off a locked transfer, it's basically telling the entire system, nobody else gets to use this road until I'm finished with my multi-step delivery. This is absolutely critical for jobs where you need to read a value, change it, and then write it back without any other component interfering in the middle. It guarantees the whole operation is secure. So we've seen the rules and the special services. Let's wrap up by connecting all of this back to why it's the real unsung hero of the performance you experience every single day.
This little rule from the spec perfectly shows the system's focus on efficiency. A single burst transfer is not allowed to cross a 1 kilobyte address boundary. Now, think of this boundary as like a postal district. This rule basically prevents a single simple delivery run from getting super complicated by having to cross into a different district, which might be handled by a completely different component. It's a simple little constraint that keeps the whole system fast and predictable.
So why does all this matter to you? Well, because this invisible, super organized postal service is the communication backbone of your devices. Its efficiency at moving data around without gridlock, without errors, and without any delay is what lets your processor fetch instructions in data billions of times per second. The speed of your favorite apps, the smoothness of your games, it all fundamentally relies on this unsung hero doing its job perfectly every single time.
And that really brings us to our final thought. AMBA AHB is a foundational piece of our digital world. But as you know, technology never ever stands still. As chips get even more packed and more complex, with specialized AI cores and way faster memory, the demands on these internal communication networks are just going to get bigger. It really makes you wonder, what will the next generation of these digital highways need to look like to keep up with it all?